So what we will do this week is look at this important algorithmic technique called dynamic programming. Okay, so I was saying that we have looked at divide and conquer algorithmic technique pretty early on in the course, and in between we have seen some algorithms using another technique called greedy technique. You may or may not have, Sakit may or may not have used specifically as a specific algorithmic technique. For example, for designing minimum spanning tree algorithms. I will touch upon dynamic programming and greedy also when I talk more about dynamic programming. So we are going to look at, this is another powerful algorithmic technique, dynamic programming. So let me start with the following example, right? Simple example of computing Fibonacci numbers, right? Let's follow this convention, starts with 0, 1, 1, 1. I want to compute, the problem I want to do is to given n, compute Fibonacci number n, right. So what's a natural way to do it? Recursively, because it's defined recursively. So one algorithm is, if n equal to 0, return 0, else if n equal to 1, return 1, else return fib n minus 1 plus fib n minus 2, where this is actually the algorithm fib n. Right. So since the function itself is defined recursively, one natural algorithm is to write a recursive algorithm like this. Okay, now how much time does this algorithm take? So what's the complexity of this algorithm? How much time does this algorithm take? Be like 2 raised to the n, okay. So how will you compute the running time? First, let's answer the question how. How will you calculate the running time? I mean, how did we compute the running time of a recursive algorithm like merge sort? What did we do? Yeah, so what you do is write a recurrence relation. Recursive algorithms are analyzed using recurrence relation, right? Because you don't know how much time it takes to compute a fib n minus 1. Let's call the time to compute fib n as some t of n. Then t of n, well, it computes t of n minus, computes fib n minus 1, for which the running time will be t of n minus 1 plus t of n minus 2. Let's say I'm computing the number of additions. When I say time, you need to be a bit clear. When we are talking about sorting algorithms, we are counting number of comparisons. Here, let's say I am computing, because that primary operation being done here is just adding some two numbers. So let me count the number of additions as my running time. Then whatever number of additions performed by fib n minus 1 plus number of additions, and then you are doing this addition, so I'm adding a plus 1. If n greater than, if n greater than or equal to 2 and 0 otherwise, because otherwise I am not doing any additions. Yep.
Is it also possible to analyze it as a recursion tree where
Yeah.
the number of children is increasing every time by the factor?
Yeah, I mean, how do you solve this? You write a recursion tree, because it doesn't fit into the master theorems we saw. So you write a recursion tree and solve this. There are various ways of solving it. You might have seen in your discrete math course. How will you solve it? Yes, so there is a way to solve this using what are called generating functions. Have you seen this? You have not, okay. I don't know why you are not attending discrete math course. So you use what are called generating functions. I'll put it out there. You can look up to solve such recurrence relations. Do you know what? So, I mean, if this plus 1 is not there, then it's pretty much Fibonacci numbers themselves. And do we know what is the growth of Fibonacci numbers? What is the nth number, nth Fibonacci number? 5 raised to the n, right? Which is, so this is close to phi raised to the n, where phi is 1 plus square root of 5 by 2. If for Fibonacci numbers, but this function is slightly different. But let's make it look like Fibonacci numbers. Okay, so let me say, yeah.
So if we are doing T of minus 1 computation, we would already know T of minus 2, right?
Okay. Okay, good. That's the part, we will come to it later. For now, we are analyzing this algorithm. If this is my recursive algorithm, how much time it takes. So, what you are saying is precisely the point I want to get to argue why this algorithm is not very efficient. Okay, but before that, let's understand what is the complexity of this algorithm. Okay, so I'm going to say can be solved. So, and if I want to make it look like Fibonacci number, let me define some f of n equal to t of n minus 1. Should I say plus 1? No, let me write minus 1. Okay. Then I claim f of n equal to f of n minus 1 plus f of n minus 2. I hope they're true. You want me to say plus 1, is it? Okay. No. Oh, I see. Okay. Because f of n itself has a plus 1, right? So if I do this, then this will be plus 2. So if I write f of n is t n plus 1, f of n is f of n minus 1 plus f of n minus 2. So that f of n looks like a Fibonacci number. So my t of n, interestingly, is slightly less than the Fibonacci number, even though this recurrence has a plus 1 there. Okay, so but anyway, asymptotically it is growing like Fibonacci number. But if you have not used generating functions, you don't know how to solve it exactly. But let's try and solve it approximately. Can you come up with a lower bound for f of n? Easy lower bound. 2. Okay, upper bound is 2 raised to n. Yeah, so lower bound, so for example, I can write like this, because this f is an increasing function. So f of n minus 1 is greater than or equal to f of n minus 2. This is relatively easier to solve, because you can keep expanding this like we did earlier. So it's 2 square times f of n minus 4 and so on. This would be like, this will solve to 2 power n by 2, because the boundary condition is that f of 1 is 0. Okay. No, you should ask this question because. So let's try and expand this, right? So it's be 2 square into f of n minus 4, right? Because if I apply f of n minus 2 is 2 at least. So again, at least. Right? There's something about the boundary condition. So let's fix it more precisely. So this will be like 2 power. So let me plug in 2 power n minus 2 by 2 into f of 2. 2 raised to? No. Do you agree with this? Right. So all I have done is n minus 2 times whatever I have done, right. So if I put n minus 2 by 2, n minus 2 times this is n minus 2, so that's f of 2. And what is f of 2? No, let's just, okay, f of 2. And what is t of 2? Is t of 1 plus t of 0 plus 1, and t of 1 and t of 0 are 0, so it's just 1. No. Okay, let's not confuse this. Tn only has a plus 1. Okay, so f should have a plus 1, so that's like f of 2 is 2. Okay, so this would be 2 power n minus 2 by 2 into 2, so that's a plus 1. So this would be 2 power n by 2. Okay, so it is okay, right? Yeah. Yeah, so f of 2 is 2. Okay, fine. So more importantly, it's square root of 2 power n, so it's exponential, right? So it's an exponential time algorithm if you blindly write a recurrence relation, which is sort of counterintuitive because in our divide and conquer algorithms, these recursive algorithms gave great improvement. Okay, so what is a better way to do it? Start from fib 0, fib 1, fib 2, just write a simple for loop and compute for I equal to 0 to n minus 1, take the last 2 terms and add it, and that will be like a linear time algorithm, right. So I'm going to just simply say simple for loop gives order n. Okay. So why is this happening? And that takes us to what he was pointing out is that, so if I expand this recursion tree the way you said, to compute t of n, I have t of n minus 1 and t of n minus 2. And then to compute t of n minus 1, there is t of n minus 2, t of n minus 3. So the same subproblem solution is computed again and again. And the way we save it here is by starting from scratch and storing the values whatever we compute, right? Because when I need to compute Tn minus 1, I have already computed Tn minus 2 and Tn minus 3. So why recompute it here? You can just store it, right? So this is one of the elements of dynamic programming. So let me just so you have overlapping subproblems. Because each recursive step is not completely disjoint, because in trying to compute this, you are doing Tn minus 2 and Tn minus 3. There are all these overlapping things, and some sort of a tabular solution. Okay, so in fact, dynamic programming is pioneered largely by Richard Bellman, and somehow programming was popular at that time. So, he wanted to get some research proposal succeeded, and he used the word programming to describe this technique. That is how the story goes. But even in linear programming, somehow the programming word is used to say somehow you compute some table of solutions and compute them. Okay. So, this is a very simple example. It is really not an optimization problem, but let us get to some interesting optimization problems where the key thing is we want to compute and store solution for some small subproblems and then build it up. Now, often the challenge is what are the subproblems you will come up with, formulate and compute solutions for, okay. And this is decided by some sort of, okay, so some sort of a recursive formulation. You want to solve your problem, somehow you come up with a recursive formulation, but do not solve it recursively, right. There will be a recursive formulation will guide you what are the subproblems you need to compute your solutions for. Okay. So, let us get to some example and really some optimization problems. So, let us look at this knapsack problem. Your input a set of n objects with some sizes S1, S2 up to Sn. Okay. And you have a knapsack with capacity or with size some W. These are integer. Okay. So, these are natural numbers, integers, and the question is find the subset of the objects with the largest total size but less than or equal to W, right. So, I have a knapsack with capacity W or size W, and I want to pick up some objects from here and put it in my knapsack as much as possible. And there are variations of this problem where you have these objects also have come with some profit and so on, but let us not, let us look at the simple version. What would be a brute force algorithm? Take all subsets, right. So, take all subsets of 1 to n, add them up. If the weight is less than or equal, total weight is less than or equal to W, keep track of it. If not, throw it out, and when you keep track of it, find the largest among them, right. So, that will give you a 2 power n algorithm because you are running over all possible subsets. Okay, now I want to use dynamic programming to solve this. Okay. So, somehow, as I said, compute opt for smaller subproblems. Now, when you say subproblem here, you could interpret it in whatever way. There are some subset of items, maybe you need to pick the largest among them. We do not know. That's usually the toughest part. Once you decide what the subproblems are, and then everything will fall in place. And the subproblems are guided by this recursive formulation. Okay. So, let us think of what would be a recursive formulation. So, and it depends on some choice you make, the first choice. The good thing about dynamic programming is that in some sense we will work through all possible solutions. So, the proof of correctness is easy because we will try in some sense. Okay. There is still one more thing I have to write it down. So let's say, okay, here is my So let's say there are these n objects 1 to n. Let me figure out, do I want to take object 1 or not? Okay, and then that will somehow determine me some subproblems. That will tell me what are the subproblems, what I have to compute. So suppose I take, suppose object 1 is in the solution. Okay. Then what would be the remaining subproblem we have to solve? Suppose somebody told you that, hey, don't bother, 1 is in the solution. Then what would be the remaining subproblem we have to solve?
W minus the size of first.
Hmm?
We need to find this S,
Yeah.
another object such that the weight would W minus the size.
Right. Now I want to find a subset of objects in 2 to n whose total, the largest size, whose total weight is at most W minus S1, right. So then let me write the remaining subset of the solution is a subset of 2 to n of largest size whose total size is at most W minus S1. Why is this true? Right. So here is my opt. Right. This is my opt set, and I tell you 1 is there. And what I am claiming is that this remaining thing is of the largest size among with whose capacity is at most W minus S1. Why is this true? Suppose there is a larger set, not larger set, but suppose there is another set of total size larger than whatever this is, then what stops you from removing that and taking that into the solution and adding it with 1, and you get a overall total larger solution, right. So this is a proof of correctness, okay, of, So I've written down, this is called optimal substructure property. Right. I am trying to prove this statement, that this is exactly what is called the optimal substructure property. If you tell me 1 is there, now you take any optimum solution. What is an optimum solution? It is a subset of 1 to n whose total size is largest that can fill up a capacity of at most W. And you told me 1 is there. So now I claim that the remaining subset in the optimum solution is the total largest size thing of capacity W minus S1. Why is that? Suppose not. Suppose there is a total larger sized another subset whose capacity is at most W minus S1. Remove this set and put that set here, combine it with 1, your overall capacity does not go beyond W, and that overall size will be larger. Okay. These 3 sentences would correspond to, this is often it's called this cut and paste argument. This shows that this is an optimum solution. This is exactly where you save on this exponential time running time, because if 1 is there, then I am going to just pick the optimum solution here. Now, I do not have to try all possible solutions. Somehow, magically, if you know the optimum solution, then you can use this. Okay. So, now this suggests what should be the subproblems we should compute. So, let us say opt, I have this opt of 1 to n, right. That is what I want to compute. So, what should I write? What should be sort of the recurrence relation? Okay, wait. Let's handle the other case. Suppose object 1 is not in the solution. Then Okay, I'm not going to write in such a detail for other examples, but let's at least for one I should do it. So suppose one is not in optimum solution, then the opt set is what? Is a subset of 2 to n, objects 2 to n, with total largest size not exceeding W. Right? Because one is not there, so you have to do this. Okay. Now I don't know whether one is in or one is not in, so the optimum would be the larger of this, right? So because this considers if one is in the solution, whatever the value, if one is not in the solution, whatever is this, and whatever the larger of the two would give me the optimum solution. Okay. So how do I write this recursive formulation of the problem, right? And what is this smaller subproblem I need to compute, right? So let's say my opt depends on 1 to n, these are the objects, and this is my capacity W, right? So here, because this guy tells you W minus S1, I don't, right? And as I go along, these SI values may change. So this suggests that there is the recursive formulation should have two parameters. One is the subset. Well, I don't need all possible subsets because it's always 2 to n in both cases, right? So this 1 to n or 2 to n or 3 to n, in general it may be opt. Okay, so this is what I want, right? So this is going to be, let's write this. This is going to be, what is it? Opt 2 to n and W, right? This case, or opt 2 to n and W minus S1, and max of this.
When you say opt, it is the larger size subset.
Okay, okay, good point. So
Because in question it's not clear to me.
it is largest turtle size. Okay, there are two. Let me write this. Computing opt value versus opt solution. Right? There are two things I am looking for. I am looking for a subset and largest total size. For now, let me just focus on, so that's the largest total size is what I call the value, and the subset that realizes is what I call the solution. Okay. Let me first focus on the value and then we will come back to how to find the solution. For now, I am just computing the number, one number which gives you the optimum feasible solution. Okay. So, I want to pack my bag of capacity W with some subset of objects as much as possible. So, this we have written down 2 to n and W. Great. Plus S1, right? Because the size includes S1 plus the remaining thing. Yeah. So, how do I know these? Well, we will somehow compute this bottom up, right? As I go along, it may be some arbitrary subset of 1 to I that would have been picked, and then I need some W minus the sum of this. So, I don't know this, since this is where I assume that these are integer capacities. So, let me do it for every integer value from 1 to W. Okay. So, what is the general thing I am interested in? I will, because this guy also changes, so this changes and this changes. So, I am going to write more opt I comma let's say some small w, this is equal to, the semantics of this is the largest sized, when I say sized, it includes the sizes, subset of I to n, right? I to n with total capacity, or total size at most this little w, right? This now I know how to compute it, because this is for 1 to n w, but in general, because at intermediate point I want some I and some value w prime, right? So this is going to be max of opt I minus 1 w or opt I minus 1 w minus si plus si.
1 to I.
We don't need it. See, we can. So that's why I'm saying what are the subproblems we need to compute requires careful manipulation like this, because this recursive formulation simply says 1 to 2 n, 2 to n, 3 to n kind of thing. So that's what I need. So this is, now we are all set. Okay. A bulk of the work is in getting to this point, and after that it's pretty mechanical. So you fill up a table. So what do? You do it in a bottom up fashion. So one important thing is the base case, right? So what is the base case? Because you are computing, so let's say, so I have a table where I have this I which goes from 1, 2, 3 up to n, and my this w which goes from 1, 2, 3 up to capital W. Right? There are these two parameters. Yeah. Yeah, you're right. Yes, thank you. Yes, but you could read it. That's good. Yeah, I'll write it bigger here. Right. Right. So now this, first of all, you need to figure out in which order am I going to fill up this table. So now the problem is to fill up this table, right? Now, what is my answer I want? Where is it sitting here? It's here. This is my final answer, right? Because this tells you opt 1 comma capital W is by definition largest size subset of 1 to n with total size capital W, right? So I need to fill up this table and eventually get this, okay? And now you look at this recurrence and see the dependence, right? So to compute I comma W, I need I plus 1 and smaller values of W, right? So we start from here, fill up. So if I want to compute some I comma W here, right? This is some I and this is some W. Then to compute this, I need I plus 1 and some smaller W's here. In fact, even I plus 1 W up to this point. Right? This table tells you if I want, I have to know, I would have computed, because we are going to use it a table form. We are not going to recursively compute this. That's exactly what we want to avoid. So I need I plus 1 up to this point. Yes, smaller values from 1 to W. Okay. Sorry. Yeah. Okay. For this W, I need this. So let's try and fill it up from last column. So this tells you which is the direction in which you're going to proceed. So let's fill up the last column. So what can I, the base case would be opt n comma w would be what? Well,
Last element if it has weight greater than W or less than W. If it's less, then we say yes.
okay, so is if Sn is greater than this W is not capital W because I need to compute this for every little w up to capital W. If Sn is greater than W or if Sn is less than or equal to W, this is easy. What should I put here? Sn, right? Because I am going to take that object. If Sn is less than or equal to W, I am going to say take that object, and so I am going to say Sn. Here 0 because I can't take this, the maximum capacity I can fill up is 0. So this is the base case for every W. Now I have filled up the entire last column because for every that fills up the entire last column. Now for the previous column you can use this because if you want to know opt IW, you take two quantities, find the and in the second quantity you have to add the SI and find the maximum and put it in here. Okay. So what is the total time for this whole computation? Again, pretty easy. How many entries are we computing? Number of entries times time to compute each entry. So number of entries we are computing is n times capital W, and how much time we need to compute each entry? Well, this recurrence tells you it's a max of just two numbers. These two numbers are sitting in your table. You just have to pull them out, add this, compare, constant time. So that's overall order NW. Okay, so yeah. Sorry? Yes. Is there a constraint? Because I don't know what table I will be able to put in here, right? The table, the values for which the W I am computing are 1, 2, 3 up to W. So if the weights are not integral, okay, it can be rational. So clear the denominator by computing some LCM and so on. Okay, you can tolerate up to rationals, but not beyond that. So we will actually, so one remark which will become clear when we next week, yeah, is that this is not a good algorithm first of all, okay. Even though it looks like a linear time algorithm, why is it not a good algorithm? Because the dependence on W is pretty heavy, right. So if the weights are, if there are only n entries but the weights are really large, then this algorithm is, it's good if the weights are small. If the weights are large, this is not a good algorithm. And next week we will see that knapsack is one of the hard problems, that there is nothing much we can do beyond this. Okay. Okay. So let's look at more examples. And as I said, you need to just get familiarized with how do I write the recursive structure, which will tell me what are the subproblems to compute, right. So let me look at discuss another problem which looks very similar. Okay. But before that, how do I actually find the subset, right? Right now, this only tells you the number. Finally, what is the total size you can take? But if I also want to find the subset, what do I do?
back from the start.
Trace back from the start.
From the opt one, the capital or yeah.
Yeah. Exactly. So typically, I mean, in this case, it's immediately you can trace back, but some other examples we can use some other information as we do this table filling to output it. So what does it mean by trace back? So I come here, I got opt NW, right? This is my optimum, which gives me a number. But I know from this computation that this is a maximum of two things, right? So this will tell me, if this, if this is larger, then I know that, what do I know?
Then we don't take the first
Sn, n, we are talking about n, right? If, because it's opt NW, sorry, opt 1W, okay, I have written correctly, okay. So opt 1W, so if opt 1W is max of some two things, right? Opt 2W or opt of 2W minus S1 plus S1, right? So those values are sitting here because everything is sitting here. So, and I made this comparison to figure out what it is. So if it is opt 2W, then I know that S1 is not in the optimum solution. If this is the case, S1 is in the optimum solution. So I can output, I'll determine this. And then I go to the next entry and so if then I do opt 2W to whatever, and that will tell me whether S2 is not there. So you can, yep. You know these value, you know this value. It's all sitting in that. Sure. Yes.
Whatever we computed, we have to again.
We can trace back. So it's like a linear time.
But we are spending almost the same time.
No, we're spending linear time. Because think of it as, I want to determine whether S1 is in the solution or not. So what do? I go to this table, it's sitting here opt to W, opt to this, and see whichever is bigger, that will tell me S1 is there or not, right? So suppose you have figured out S1 is not in the solution. Then you know that it's actually opt to W. Go to opt to W, it is a maximum of two quantities, and based on that, you will know whether S2 is in the solution. So you're just jumping one at a time. So in order n time, we can find the subset. By, yeah. Sometimes we may actually need to keep some extra information as we build on to figure it out. I mean, we could also do it, yeah. Okay. So I think, yeah. Okay, so okay, maybe set cover is so similar that I will leave that as an exercise.
We could have maintained some pointer for determining which one was the bigger.
Yeah, you mean exactly as you have built on. If you, whenever you find the max is there itself you can even output. If it's this case, then I know that I am going to output S1. Otherwise, I won't output it. You could do that also in the same pass. Yeah. Okay. Now let me walk you through set cover. Okay. So here is a problem set cover, whose input has, there is a universe, some finite set, and the family F containing, okay, so let us say it is N, M subsets of U. And the question is, find the subfamily F prime of F such that union F, F in F prime is the universe. That's okay. So let me give an example. So I have a universe of, let's say, some 5 elements, and I have a family which consists of these sets. So that's a universe. I have a family of some subsets of sets, and what I want to find is just give me some small number of sets from this family whose union covers the universe. Okay. So this is a very central problem that can model a lot of covering problems. Okay. So is the problem clear? I want a family of small size. That means I want a small number of sets from this F whose union covers the entire family. So in this example, it would be like you need 3 sets. Yeah, so I might pick 1, 3, 4, 2, 5, 6, 7. Okay, yeah. And there are other subfamilies also with 3. Right? I could do 1, 2, 3, 4, 4, 5, and 6, 7. There are several combinations of 3 sets that together cover the entire universe. Okay, so this is the problem. Again, let's have a benchmark brute force algorithm. What would be a brute force algorithm? Yeah. Yeah. So take all, a brute force algorithm would be, I mean, yeah. So find the subfamily. So try all subfamilies of my family F that contains M sets, and then take the union and see whether it covers the whole thing, and then keep track of the total number of sets you have picked in these sets that cover the universe. So this will be like order 2 raised to m, right, times something to take the sets and doing the universe. Now, M could be very large because M is a family of subsets of the universe. So M could even be like 2 raised to n, right. So this is somewhat of a bad running time, and we want to improve it to 2 power n using dynamic programming. Okay. Yeah.
Finding any value is okay, or should we find the specific F primes with the 2.2
Okay, wait. Yeah, a subfamily of smallest size. Sorry, yeah. It's clearly an optimization problem.
So in brute force, you are drawing all the possible.
Wait, so is that clear? Yeah, it's a subfamily of the smallest size. Okay. Yeah. So the brute force algorithm is I take my F and find some subfamily, right? Run over all subfamilies of F. Since this has m sets, number of subfamilies will be like 2 power m sets, 2 power m minus 1, maybe I won't pick the empty family and things like that, but in the order of 2 power n, 2 power m subfamilies, and then I take the union of them and see that cover the entire universe, and if it does, then I will keep track of the number of sets in the family I have picked, and among all of them I pick the one which is the minimum number of sets. So, that is like 2 power m algorithm, right. Now, we want to improve it to so this is some polynomial runtime which I am going to ignore. Okay. So, this has actually a notation. So, let me use that, it is O star 2 power m, meaning I am ignoring some polynomial function in m and n. So, we want to improve it to O star 2 power n. So, it is like 2 power n times n square or something.
That was for taking the whole thing together and checking where it equals.
Yeah. So, what is this time for? Well, once you have a family, you just take the union of these sets and check whether it covers U or something, right. So, just the union of the sets. Okay. So, if I want to use dynamic programming, so I need to think about what are the subproblems I have to compute and how do I write some recursive formulation for this, right. So, let us say my family F has sets S1, S2 up to Sm, and I have a universe U. Okay. I use the same symbols like knapsack. So, so what is the choice you will make? What are the subproblems you will get? Yeah. So how?
So I'll try to order all this like members of the family as the.
I call them S1 to Sm.
Okay, yeah.
Call them S1 to Sm.
And we do the same thing as before. We check if S1 is there or not.
Yes. So if S1 is in the opt, then what is left is to cover U minus S1 using smallest subfamily of S2 to Sm. And if this is the optimal substructure property, this needs an argument, cut and paste argument. If not, take S1 and whatever you collected, that will give you a smaller family. If S1 is not an optimum, okay, maybe try and use a different color and see if we can. If S1 is not an optimum, then what is left is to cover U using S2 to Sm. Okay. So, what would be your subproblems? So, let us say we will say opt I some S, right. This is simply saying I am going to use Si plus 1 to Sm, and this is saying cover this set, right. So, S, so I is going to be this and S is a subset of my universe, right. So, cover this subset of the universe, not the entire universe, because the smaller subproblem is going to cover some U minus something. So, it is some subset of U. So I'm going to try and compute this bottom up for all subsets of U. So S is a subset of U, and using sets Si to M, Sm, right? So I varies from 1 to M, S is a subset of U, and I want to do this, and this tells you from here is equal to opt. So Si is in the solution or Si is not in the solution, then use I plus 1 to M to cover S. If Si is in the solution, then use I plus 1 to M to cover S minus Si. And what do I do?
Should be plus 1 from T.
Thank you. Yes.
Minimum.
Minimum. Exactly. Right. Somehow, the first choice, I'm going to try all possible choices. So, the choices here is S1 is in or out of the choices. I'm going to try all possible choices, and that determines the subproblems. What are the subproblems to compute and figure that out, right? Yeah.
Base case here will
Okay. What is base case, right? So it tells you, first of all, I go eventually, what is my goal? What do I want to compute? Opt 1 U, right? I want to use S1 to Sm to cover U, right? So it tells you I have to do in decreasing order of I, right? Because eventually I will stop at I equal to 1. So base case would be I is equal to M, the last column, right? Because I am computing column by column. If I is column number, I am computing. So what is the base case for opt M S? What is it saying? That I want to cover S using only Sm. So this would be what? I want to cover S using Sm.
is equal to S.
You need equal to or
Subset is
what is a subset?
the members are contained in the
S is a subset.
If S is a subset of Sm, then one set is enough, right? If S is a subset of Sm, then because I am trying to cover S using Sm. So Sm contains S and more, I pick Sm and it's 1. If the Sm is, if not, yeah, infinity, right? Because it's a minimization problem, so I have to say infinity, not 0. That's the base case. That's it, right? So you somehow figure out a choice, right? Here the choice function was, should I take S1 or not, or Sm or not, right? That tells you some subproblems, optimum substructure, recursive formulation, table, base case, we are done. And what is the running time here? I have removed the formula, it's very simple. How many table entries you compute and how much time it takes to compute one entry. How many table entries? Well, this tells you. For all values of I, for all values of S, how many values of I are there? M. How many values of S are there? 2 power n, because that's the number of sets. And to compute each entry, it is just a min of 2 quantities which are already sitting in my table. So that's constant time. So my overall running time is m times 2 power n. Okay.
then 2:n can be much bigger than the size of the family.
Yeah, you're saying m times 2 power n can actually be worse than this.
No, what I was saying is 2:n can be much bigger than the size of the family itself.
Yeah, yeah.
Yeah. So do we need to find so many of the values?
Yes, because you don't know what subset you will be asked to cover. This U minus Si could be any combination, and I don't know that because it depends on what is being picked.
Subset is equivalent to left side. Is it? There is like
The algorithm idea I pointed out, either you take the last object or not. Here it's like take the large set or not, but I don't know if there's any stronger analogy here. Okay, now this 2 to the n is also not a great running time, but here is the news. We don't know anything better than this, okay, more or less. And there is a conjecture that you can't improve this 2 to the n for a set cover. Again, it's one of the hard problems. So, we know we strongly believe that we don't expect a polynomial time algorithm, but something stronger that you don't expect something better than 2 to the n. These are conjectures, but okay. That, no, in this algorithm, yes, but the conjecture is that you can't improve on the exponent better than 2 power n. Okay, so again, you need to get a feel and experience with how do I break it up into subproblems. So let's do one little involved example, and that is again I'm only computing these numbers. If I want to compute the set, same ideas, like you can trace back from the table to get back the actual set. Okay, so this example I am not going to give the complete details, but let me define the problem. It is optimum binary search tree problem. Okay, so you are given in input your keys k1 less than k2 less than kn, and I want to build a binary search tree on them. Okay, so we know we have seen red black trees, B trees, there are various kinds of binary search trees you can build so that the search time is optimized, right. So in fact, search time is logarithmic. Now, I am also going to give you some more information, and I am going to tell you that frequencies, right. This k1 is going to be accessed f1 times, k2 is going to be accessed f2 times, kn is going to be accessed fn times. Okay. And let us also write down gap frequencies. G0, so anything less than k1 is going to be accessed G0 times, anything between k1 and k2 is going to be accessed kn times Gn minus 1 and Gn. So this is number of times. So Gi is the number of times a key between ki minus 1 and ki is accessed. No, ki and ki plus 1. No, what is G1 is between F1, yeah, ki and ki plus 1. Okay. We'll look at an example and then you'll get a picture. So what is it? So what I'm saying is, my goal is, so I have done some, so let's say these are some characters in my English words or something, okay, and I want to organize you to, I want you to organize these n words in a nice binary search tree such that the total cost of accessing is minimized. I have done some statistics and I am telling you that this key is accessed more often than this key, So, not your good old standard red black tree may not be an optimum way to minimize the total cost, because I am not interested in minimizing the maximum cost. I am interested in minimizing the expected cost or the total cost, right. So, some key is accessed more often than not, then maybe it is better off to bring that closer to the root. So, there are many ways of organizing a binary search tree and these n keys. The question is the output. So, this statistics tells me that K1 is the total number of accesses is some summation Fi plus summation Gi. That is the total number of accesses I am going to do on these keys. F1 time I am going to access K1, F2 times K2 and so on, and any key less than K1 is going to be accessed G0 times and so on. So, this for this total summation Fi plus summation Gi accesses, minimize the running time, organize a binary search tree that minimizes the running time. So, that is what is called the optimum binary search tree. So, find a binary search tree. I do want a binary search tree because I am going to do search according to the binary search tree that minimizes total cost. Okay. And what is the cost? Because in your binary search tree, your K1 is here and at a distance of L from the root, then the cost to access K1 will be L times F1, because you are going to access this K1 F times. So, okay. So, you add all this cost and you want to minimize this cost. So, let us see a quick example which I just made up. Let's say I have these 3 keys. There are 100 accesses and if these 3 keys A less than B less than C, A is going to be accessed 10 times, B is accessed 20 times, C is accessed 30 times and these gaps are accessed 10 times. Okay. So, what would be a natural greedy choice here? The guy who is accessed maximum number of guys, put it in the root maybe, right. That could be a greedy choice. So, let us try that, right. So, greedy would say put 30 C here and then I am going to put B here and A here. Okay. So, this would be one choice of a binary search tree. Another choice would be like this, right. And you can compute the cost for each of this. So, the cost here would be for C I am going to access 30 into 1, for B it is 20 into 2, for A it will be 10 into 3 and for this gap, now I am going to access the key comparisons. So, I will compare here and it will tell you less than A and it is a nil pointer. So, it is 3 into 10, 3 into 10 and here it will be 2 into 10, 1 into 10. That will be the cost for these gaps. There are 4 gaps, right, because C is accessed 30 times and all the 30 times I just go in one comparison, I will find the answer. So, the total cost, search cost for searching C would be 30 into 1 and 20 into 2 and so on and so forth. Okay. So, you add this cost. Similarly, you add the cost here. There are many binary search trees and out of all the ones, the one that minimizes the total cost is what I am interested in. Okay. So, let us see how I would compute it using dynamic programming, what would be a recursive formulation, what are the subproblems, base case and then we will be done, right. So, what is the first choice you want to make? Root, right. So, so you will so let's say try ki as root, right? Some ith key. There are n choices. I'm going to try one by one. Now, once I fix ki as root, let's say, what can I tell you? What can you say about this tree? It is an optimum substructure property. It is an optimum binary search tree on the keys 1 to k minus 1 and also the whatever the gap. And the gap G0 to Gi. Right, so this whole thing okay, Gi minus 1, right. And similarly, this would be an optimum binary search tree for Ki plus 1 to n and the gaps Gi to Gn. Okay. Now, how many different binary search trees are there? Before, I mean, suppose I just do brute force. Well, you can get that from this picture.
We can change root every time with n.
Yeah. Yes, exactly. So, number of this binary trees, or rather binary search trees, would be summation I equal to 1 to n, right, because I just put ki as the root. Once I put ki as the root, I am, what is this term here? The number of binary search trees on 1 to I minus 1. So, it's, so if I call this as T of n, it will be T of I minus 1 times, right, because for everything here I can choose this here and that will be an overall binary search tree. So, this will be T of n minus I, okay, some over I, because it varies over I because as it increases this. Do you know generating function? So, you can again solve this using generating function, and the solution to this is a popular number called Catalan number, which is roughly 2 power n by n power 3 by 2 or something like that. Okay, a brute force algorithm would be to compute, run through all these trees, compute the cost and pick them in, but we are not going to do that because we are going to use the fact that it is an optimum substructure property, right? Because on this portion, why do I want to compute all possible trees? I just pick the optimum. If ki is the optimum in the optimum solution, right? This is a flavor of if Si is picked into my set cover or if ith object is picked into this Si, then I have the following subproblems. What is the subproblem? If Ki is the root of the optimum subsolution, then this tree must be an optimum binary search tree for 1 to I minus 1 and this must be for I plus 1 to n, otherwise cut and paste, right. Okay, so now this tells you what, so now you run through all possible root values, that is the final solution. So, what are the subproblems you will compute? Yeah, so the problem is that if you do 1 to I and I plus 1 to n, then when I come here, somewhere and again I have to choose a root and this one be 1 to something. this would be, say, let's say 1 to j, this would be j plus 1 to I, not j plus 1 to n, right. So, basically the subproblems are for opt I to j, right, for your, gi or ki, k plus 1 to kj and the corresponding gaps, compute this for opt ij. Okay. So, that is a subproblems. The base case would be, opt I to I or something like that. There is only one key, you just put it in the root and you will get it, right. Basically, this distance is increasing, right. So here you will compute this table, 1 to n and 1 to n, and you are doing it in a diagonal fashion in some sense, because the diagonal it will be 1, 1, 2, 2, 3, 3, and then you are basically going to compute this upper diagonal thing, because I to j, where j is greater than I or equal to I. So, you are going to compute this upper diagonal thing, so you will do diagonal by diagonal, and what would be a recursive formulation for opt ij? Let me write a very high level description. So, opt ij, this number would be, you are going to try all possible keys, right, and so these keys are anything from I to j, and I am going to, let us use L. So, I am going to use KL as my tree. So, there is this L, and here cost of or opt I to L minus 1 plus opt of L plus 1 to j. What else happens?
Height is increased by 0.4.
Great, right. So, whatever the cost of accessing these guys is here, whatever the cost of accessing these guys is here, but for the overall thing, I also have to increase this FL, right. The L times I am going to access, L is brought in, L times, because this L is not included here, plus every key, the cost has now increased, the height has increased by 1. So, if you have used whatever, if there was some P and you would have used Fp times some D, now you should say Fp times D plus 1. So, there is a summation of all the frequencies here which you have to add, okay, and including FL, this turns out to be a very nice thing. It's summation Fi plus Gi in this range. Okay, so it's going to be min of this plus this. Okay, you have a base case, you have a recurrence relation, do a bottom up diagonal by diagonal, because you just start with 1, 1, 2, 2, 3, 3, 4, 4, 5, 5, and then you slowly increase to 1, 2, 1, 3, make this distances 2, and that is what this gives you this. So, this computation is just computing the weights. So, let us say we will do it incrementally in some order n square time, okay, because for every pair you want to compute it in. So, that is an order n square. So, if you omit this, it is an overhead, then the number of entries you are computing is number of entries, why is it n cubed?
You mean all possible subproblems?
Yeah.
Yeah, it will be all substrings, right? So,
Okay, n cubed, yeah, okay, right. For each I there will be n, it's n square. No? You fix an n first I, there will be at most n. So, n square such things and n square. Right? but it will be order n square. Order n square entries. Order n square to compute this is a one-time thing. Now to compute each entry, how much time? Order n. Because you are computing the min of some n different entries. This looks like constant, but you are computing the min of n different entries. So that's overall n cubed. Okay, this is actually a slight improvement to this, to n square, using some other ideas, but anyway, so I just wanted to give you this slightly involved problem, and it's all about try all possibilities. Now you pick a choice, it tells you what subproblems to compute. You have to be careful about subproblems, write down the recursive formulation, and this is it. Okay, let's stop. We'll see more examples next time.